Hi, Stefan.
Hi, Phil.
You use this on a regular basis, this chart?
Yes, we do. It's
What are you
one
studying?
of the main tools in nuclear physics, and I'm doing nuclear astrophysics.
Astrophysics,
Yes.
right? Yeah.
So we are interested what goes on in stars and which type of reactions go on in stars.
So that's where these things get made, right?
Yes, that's where all the elements,
Yeah.
except for maybe hydrogen and helium, are made. So basically all of us are product of stellar evolution.
Right. I didn't evolve from a star. A star exploded.
For instance, the star made the element, the elements and the isotopes you or or everybody is made of. Yes.
When you talk to an astrophysicist, they make it sound so simple. Oh, yes, hydrogen forms helium, helium forms carbon, etc. But actually, you look at this, and there's so much more going on.
Yeah, there are several thousands of these little squares, so several thousands of these isotopes.
Yeah.
And
so therefore, several thousand reactions happening in a star.
In stars, yes.
So exactly what is this on screen here?
Oh, that's the chart of nuclei, which was made by by Ed Simpson.
Yeah. It's a bit like a periodic table.
Yeah, a little bit like a more extended periodic table. You know, where in the periodic table you just have the elements.
Yep.
All the elements we know.
Yeah.
But what it doesn't show, the periodic table, is that you also have different isotopes of elements. So nuclei consists of protons and neutrons.
Yeah.
If you add a proton, you end up with a different element.
Yeah.
If you add a neutron, you end up with the different isotope of the same element.
Right.
So the chemical behavior
Yeah.
basically stays the same, but it's a bit more heavier.
A bit heavier. And that's what this one shows.
This one
so
shows...
the normal periodic table kind of goes across like that.
Yeah.
For each one of those,
you have a whole row
right
in this one.
Okay, so if we pick germanium here,
yes.
What is the black ones?
The black ones are the stable ones. So you have radioactive one, which decay with a certain time constant, and you have stable ones, which essentially live.
Right. So if we pick germanium here, then there are all these 59 right through to off the scale.
Exactly. Yeah. So
and it's just the same number of protons, but
it's the
different
same number of
neutrons
protons,
for each one
same
of those.
chemical element, but different number of neutrons.
And why are some of them taller?
In this case, this chart shows the half-life. That's this time constant I talked about.
Yeah.
So how long-lived are the different isotopes?
Okay, so this 76 germanium is
long-lived. Yeah. And the black ones are the stable ones, so they essentially live forever.
How did your work relate to astrophysics?
What we try to study is all these different reactions and do the math and the computer simulations to find out how much of a certain isotope is made, at which stage of the star it's made, so in what conditions.
And I guess each one of those is going to turn into something else. So is
most
that what you
of
mean
them
by a
do.
network? They kind of form a chain and some go this way and some go that way?
Yeah, exactly. So they interact with neutrons and protons in the star, and by that build a different isotope or different element. And they also decay, because as we said, not all of them are stable. So they decay back to the stable ones.
Right.
And that's essentially an evolution from the lowest masses, which hydrogen, helium, all the way up to, if you consider also explosions and explosive scenarios, all the way up to the heaviest, like uranium, plutonium.
Okay, so the uranium that's in the ground in Australia was formed in an exploding star by
some kind of explosive stellar scenario. So if it's supernova or if it's merging neutron stars, that's still an ongoing debate.
Okay. So what are you working on?
I look at some of these reactions, specifically or mostly neutron capture reactions. That's when certain of these isotopes capture a neutron and move one place to the right. So the element stays the same,
but change isotope.
Change the isotope.
Yeah.
And what we try to do, so as I said, the theoreticians try to do these network calculations, and we try to give them anchor points for the most important or the experimentally accessible reactions.
Right. So you're doing these reactions in the accelerator here.
We are doing the measurements of the reaction products in this accelerator, and we are simulating the stellar conditions with other accelerators or with nuclear reactors.
What do you mean by that, simulating stellar conditions? You mean hot and pressure?
Yeah, essentially the
Explosions.
Explosions are experimentally very difficult to access, or not at all, because you don't get the densities and the energies which you need. But what you can experimentally access is the normal life of a star. So when it's not exploding, just burning his nuclear fuel. Right? And you simulate the particle energies and bombard your targets with these particles with certain energies. And then you know what you had in the beginning, you know what you bombarded it with, and then measure the outcome. So how much of the product have you produced? And by doing some math and figuring out the ratio of what you had in the beginning, what you have in the end, you can work out the probability for that certain reaction.
Right. So you're doing one reaction in this table, or a few?
Yeah, a few reactions.
So what do you reckon? What's your estimate across the whole table? How well do we know? Do we know 50% of the reactions, or maybe we know 10% of them really well?
No, I don't.
20%.
I doubt 50%. Maybe
less than
like
50%. You reckon?
Yeah.
Yes. Okay. So there's still plenty to work out.
Yes.
You've got a busy afternoon ahead of you.
And also, it's definitely a busy week, and probably depends on the funding. Busy life. Yeah. So it also depends on the energies you're simulating. So stars are not. It's not one single energy a particle can have in the star. So you need those probabilities for different energies as well, and not all of the reactions, because some of the stuff is very short-lived. So you can't access it experimentally, or you don't get enough of the material, so you can bombard it with neutrons or protons or whatever you want. Right?
Wow.
So that's the tricky part. So we focus on the reactions where we have enough target material, and on the reactions where we actually can measure the reaction product.
Right.
Yeah.
Okay. And that's enough to give you something to.
Yeah, that's something
hang on to.
to hold on. Yeah. To hold on to.
Right.
But essentially everything which is very far away from this line of stability, so the black squares, it gets more and more difficult to access those nuclides.
Right.
As long as you're here, you can irradiate the stuff. But once you get out here...
Yeah. Most of these are not very tall, meaning they're very short.
They're very short-lived.
Okay.
I mean, there are different techniques you can access them.
Yeah, okay.
One would be decay counting. So you produce, for instance, something which is radioactive, that decays, and you can count those decays, which gives you a number for how much you have produced.
Yep.
A different one is you can do everything online, so you do the irradiation of stuff, so you bombard your target with something, and immediately measure the reaction products, which can be photons, which is high energy light.
Yep.
It can be also the produced nuclei themselves. Or what we do is so-called accelerator mass spectrometry, which is single atom counting. So that's mainly used for really long-lived stuff, where you end up with half-lives of several thousands to millions of years. And it's very sensitive for those kind of nuclides.
Right. So what are some examples of that kind of thing you look at?
One I'm working at the moment is zirconium-93, which zirconium-92 is a stable isotope of zirconium, and 93 is a long-lived one with some 1.6 million years of half-life, and that's fairly challenging for accelerator mass spectrometry, and hence is interesting for developing the technique, but it's also interesting for some stellar scenarios, because it's a reaction which happens just on the border between two different stellar environments, right? So two different types of stars.
Right. So it's going to give you an bit of information about whether it was one type of star or the other. Different supernovae or?
No, it's not supernovae. It's during hydrostatic burning, so in the static phase of a star, but it's neutron reactions, so that actually goes above the iron.
Right, I see. Yeah, okay. So what you're doing is you're measuring zirconium-93
with accelerator mass spectrometry. Yeah.
And do you make that separately and then run it through the accelerator, or does it get made along the way?
You make that separately, so it's two parts of the experiment.
Right.
You do the irradiation, the bombardment of your stable target, which is in this case is zirconium-92.
Yeah. And
then do the measurements here at the ANU with our 14 Megavolt accelerator, where you do single atom count, filter essentially everything out, what's not zirconium-93, and then count atom by atom.
Okay. And because you know how much was
there in the beginning, and you know how much neutrons, how much bombarding particles you had, you can work out what the probability is.
Okay. Yeah.
And one thing which might be also interesting for a more down-to-earth application in the case of zirconium-92 is that zirconium is used in nuclear reactors for cladding because it's chemically and the resistivity, the chemical resistivity and also temperature resistivity is very high. And also because the probability to react with neutrons is fairly low. But actually that probability for those energies of neutrons is also not very well known, which is surprising because it's so commonly used. And it's also produced by decaying uranium.
Right.
So, and to get a handle on how much radioactive waste this thing, the zirconium-93 you produce, you also could use
in the walls of reactors with the zirconium
for
cladding.
instance, in the cladding, or the fuel itself.
Wow. Okay, that's important stuff to work out. Yeah.
So you have the stellar applications, and then you have more down to earth.
Yeah. Great
motivation.
Thank you.
Welcome. You're welcome.